So, guys, what I want to do is I want to talk very briefly about why why that graph looks like a triangle, and then we're going to move on to something a little bit different because I feel like you guys are probably Algebra 2'd out. And I was thinking about what would be sort of useful, and one of the sections that I'll introduce the section a little bit, but the one section that I was gonna do had to do with fractions and simplifying and things like that. And then I thought, well, hang on a second, we don't need more Algebra 2. We've had enough Algebra 2. But I used to teach a class. For a couple of years, I taught a class here called Math for the Trades. And it died just because we didn't have enough people signing up for it. And then we were trying to bring it back next year because we had some people, but it looks like it maybe isn't going to happen. But there's all sorts of cool stuff that is applicable to things that you might be leaving here to do. And I thought, you know what? Instead of teaching algebraic fractions, we're going to talk about fractions for the next few days, but we're going to talk about them with a focus on how to use them on all these different things that you might be going out and doing. So trades type stuff, whether you're going to be a plumber, an electrician, or a nurse, or I've got all these example problems from that trades class. And I thought, you know what, the heck with it. Let's just look at that. And I'm hoping that over the next few days, you guys will be looking at these problems, and instead of thinking, ugh, more math, ugh, more math. Instead, maybe you'll be looking at it and going, oh, hey, well, that's interesting. I never realized that you could use math to do that kind of thing. And then when you walk out of the door, maybe you get to wherever you're going job-wise and think, oh, yeah, I remember when we talked about these in Mr. Armory's class. Yeah, this isn't that bad at all. So it'll be a real focus on practical application, but it's also going to be a review of how do we use fractions, because you can use fractions all the time is a reality in life. There's fractions everywhere. And it's nice to be able to look at them and go, oh, yeah, I know what to do with that. So the first thing I want to do is I want to talk about, however, that 3D. I want to finish wrapping up this 3D. One variable, x equals 3. Do we agree that was just a point? Here it is. And I can change x by moving back and forth on the number line. Fair enough? Mm-hmm. The point. There it is. X equals 3 is the end of my finger. When we went to a line, we took x equals 3 and we stretched it. And now we got x and y, agreed? And it could be straight up and down. X equals 3, y is anything, but it could be at some angle. Or it could be x equals anything, and then y is equal to some number. But it was a line. What do we get when we stretch a line?
A longer line.
No. If we stretch a line like this, we get a longer line. Although since this line was infinite, I'm not sure how much longer it could get. What do we get if we stretch a line this way?
A plane.
We get a plane. So if you think about one dimension as a point, and you think about two dimensions as a line, does it make sense that 3 dimensions might end up being a plane? Or we could even just, draw it as a rectangle. But that still doesn't let us see, why do we get that triangle? So I'm going to be right back, because I should have gone and grabbed it earlier. But I'm going to be right back. I got to run across the hall and grab something.
That we can actually put in the actual life. Yeah.
Yeah, because I tried to get into trade
Same here.
this year,
And there was no.
we didn't have
Yeah. We're over here with like. What? That's interesting.
What? There's your marshmallow graph, isn't it? And so if we had come up with solutions, remember we need 8 of these to make a whole graph? We talked about that at the beginning. We needed 8 of these little sets of axes to make a whole 3-dimensional graph. Well, think about where's all these other points. Well, they're back in this section here. And then there's points over in this section here. And there's points in this section. There's points in that section. And if we think about all 8 of them, what we're seeing with your marshmallows is just a little tiny slice. And of course, it's going to be shaped like a triangle because it's bounded by the 3 planes. There's the x-intercept, there's your z-intercept, there's your y-intercept, and it's bounded by each of those 3 planes. And if something's bounded in 3 sides, it's going to make a triangle, right? We cool with that? Does that make sense? What we were looking at there? And then, of course, I could rotate it around, and if I rotate it just right, what do you see now? When you say flat, what do you see? Do you see flat?
2D.
You see a line, don't you? If you look at a plane end on, don't you see a line? What do you get if you look at a line end on? You see a point or a dot. Cool. Jack, frowny face. Here's your lines.
Yeah,
What do you see? What do you see?
a point, but like. What?
You guys remember a problem from, yeah, I know, better point than this, but I like this one. I think it's long and I can hold it. Guys remember a problem from algebra where, and you may remember because of the names, Etube had a tree farm, and some of his trees got diseased. And the tree farm was laid out like, in a grid, a row of trees, 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 row of trees. And depending on where he stood, if he was looking this way, he could only see one tree because it hid all the ones behind him. This was part of the idea that when you're talking about lines, that they're all in a row. And if you stand and you look at the row of trees, the only tree you're going to see is the nearest tree because it hides all the ones directly behind it. And I know when I taught algebra, well, you guys have seen it. They decided to diversify the names, and so then half the names in there, you're like, wait, I didn't even know how to say that. Is that really a name? But Etube was the guy who had the tree farm. And so I remember everybody getting a kick out of, never heard that name before, not quite sure how to say it. But then talking about his tree farm. So, all right. Questions? Guys, that is the end of 3D graphing.
Oh, I thought we were gonna do like the bead thing,
Oh, we're gonna do what?
like, you know, like the things that were outside had like the beads on it.
Things outside of the keys on. I have no idea what you're talking
It
about.
was like a piece of paper, or it was like they're hanging on the wall,
You're
but
not
it was like different graphs.
Oh.
Oh, no, that's something completely different. That was actually, yeah, no, that was something completely different. All right, so we have today and tomorrow, 2 days. We have 5 days next week. That's 7 days. We have 2 days a week after that. So that's 7 days. Right? I was just waiting for somebody to say, but Mr. Harmony, that's 9, not 7. Guys, here's my plan for the next week and a half, and I'll just advance notice. We're not going to do any math at all on those last 2 days.
Yeah.
That's a Monday and a Tuesday, 14 and 15. We're not going to do any math at all. I'm just going to find something fun to do. And I don't mean like fun, like math teacher fun. Did I tell you about the t-shirt I saw? It said, I like to party. And then in little tiny letters, it says, and by party, I mean teach math.
that seems like a trick thing.
I almost bought it, except I don't wear t-shirts to school, so then it would be wasted. So, so we've got 7 days of math left. And this is going to start out a little scattered because I was just thinking about this morning. I'm not 100% sure how this is going to go. I think today will be a little bit scattered, but I'll try to do the best I can because I'm sort of winging it and figuring it out. I think tomorrow will be better. And then all next week, it'll just keep getting better and better and better. But here's the way this process is going to look. We have 4 sections. I need new batteries. We have 4 sections that I want to cover. And the 4 sections are basically simplifying fractions. This is all fractions. And I'm going to give you some tricks. I'm going to show you some things that's going to make life easier. And then we will review the process in case you're going, oh my gosh, I don't even remember fractions. That was so long ago. I get it. The second is going to be multiplying fractions. The third is going to be dividing fractions. And the fourth is going to be adding fractions. Now, why don't we have subtracting on there? Well, because adding and subtracting are the same thing. It's just adding a negative. So adding will include subtracting. Why is there dividing when you could say, well, multiplying and dividing are sort of the same thing? They sort of are, but there's a trick to turn dividing into multiplying. You may or may not remember it, but we'll talk about it when we get there. And again, all of this is going to be focused on practical applications. I have put together a worksheet that will be your homework, and it's divided into 4 sections. It's divided into A, B, C, and D. I may split it up before I stick it up on the internet, or I may just stick it up as one worksheet. But what I'm going to suggest that you do is only do the section that I assign. So when I assign it, it will say, do the worksheet part A, and then it'll say, do the worksheet part B. So you don't necessarily go rushing off ahead and then not get it, okay? Or maybe you do get it. That's no big deal. But so I want to just let you know that when you see the worksheet, it's going to be a fairly big worksheet, but don't like freak out and then go, oh my God, I don't know how to do these problems. It's like, well, yeah, because we haven't talked about them yet, because we're still on that one and you just tried to do that one. All right? Questions about the process or the layout? Okay, let's start by reminding ourselves what a fraction means. And I would love it if we were taking notes, just so that when we go back and we see these problems, it's not just I don't know what's going on here, I don't get it, I hate fractions, patty face, stomp your foot, hold your breath. We'll be able to just say, oh, no, I don't have to do any of that stuff. I can just flip back and look at my notes. So first of all, what does a fraction mean?
Part of a whole.
Guys, that's about as simple as I can make that. The top is how many of them you have. The bottom of it is how many make up a whole. So For example, if you take a board, each of those pieces is one out of, I cut it into 3 pieces. The bottom means 3 pieces. The top tells you that this is one of them. So if I need 2/3 of a board, what we're really, if I were to measure it out into 3 equal pieces and then just take 2 of them and cut off the rest and throw it away. Okay. Now, guys, some of this you're going to be like, yeah, Mr. Armstrong, I know, I get it. But I think this is good reinforcement and good review of what we're going to be doing in fractions. Because I think where people lose it on fractions is when it's just like this number that has 2 bits and the bits don't have any meaning. And I think it's really helpful in math when you understand, oh, when I look at that fraction, this is what it means. I think it's the same with all the stuff that we studied this year. And I tried to make a big deal out of, like, the quadratic is a parabola. And when I solve it for x and factor it, I'm figuring out where the parabola touches the x-axis. And it makes it a lot easier to think, okay, well, why am I doing that? Oh, yeah, because. So if we think about a fraction as parts of a whole, then it's just a lot easier to visualize. So let's think about flipping a coin. I'm going to flip a coin. What fraction represents the heads flipped, or the number of times that I flipped heads? What fraction? Don't shout it out, just think about it. Jalen?
7 out of 13.
7 out of how many?
13.
You guys are great. This was the heads. And this was the total. Okay. Do another one. A paperback book costs $6. I have $5. What fraction of the purchase price do I have? Price? I have 5/6 of the price. When you see a fraction, this is what I want you to be thinking about. I want you to be just thinking to yourself, oh, look, there's a total number of parts, and that's how many I have or need or want, whatever it is. I have 5 out of the total of the 6 that I need in order to buy this book. We will assume no sales tax for the purpose of this discussion. Little side story. When my nephew was, this would have been 4 years ago, he was 7 or 8. And for Christmas, I had just told my nieces and nephews, I gave them each a little certificate that I made that said, I'm going to take you shopping. You get $20 or $25, and I'll take you wherever you want to go. And I'll buy you, I think it was $25 worth of stuff. Rather than my buying stuff that they didn't want. I don't know what they want. They're kids, you know. Who knows what they're into this week. So I take my nephew shopping, and he wants to go look at Lego sets. And we're at Target, and he's looking at the Lego sets, and he's figuring out he could buy this like one big Lego set, but then there's like $3 left over, or he could buy like 3 small Lego sets, and he's actually doing all these calculations. It's totally awesome watching him go through and, you know, how do I maximize my Christmas present? You know, if I buy the big Lego set but have more money left, but if I buy the 3 small ones, and then about halfway through all this, and I'm just hanging out. He's been looking at this stuff for 10, 12 minutes as he goes through and figures out what he really wants and what's the best deal. And all of a sudden he stops and he says, Uncle Kevin, yeah? Do I have to pay the tax? And I said, no. Ignore the tax. It's $25 worth of stuff. I'll take care of the tax. You find $25 of it. And I just thought the fact that this like 7 or 8-year-old kid was just like, he was doing so good at all the math and all, do I have to do tax? Because he knew there was this thing called tax and it was more money. So anyway, that was fun. That was super cool. All right. So let's look at 4 questions real quickly. Make sure that we're good with this. Let me find block off. Here's 4 questions. And the question on each is what fraction goes into the blank space, and then we will move on to the next bit. You don't have to copy down the questions, but you might want to write down the all right, there we go. Jot down the answers, because if you have to figure it out when I call your name, then that's really annoying for everybody else as they sit and wait for you to figure it out. Lose. A, if we divide a length into 8 equal parts, each part will be what fraction of the total length? 1/8, agreed? Excellent. Andrew, 3 of these parts will represent what fraction of the total length?
3/8.
You good? 3/8. Gwenny, 8 of these parts will be what fraction of the total length? 8/8. You might be tempted to reduce that to 1. I'm not a big fan of actually reducing that in this situation because 8/8 tells me that I have 8 parts out of 8 of them, and whereas 1 just tells me I got a whole. Okay, that's actually less informative. Cool. And last one, 10 of these parts, Capon, 10 of these parts will be what fraction of the total length?
Either 1, 2/8 or 10/8.
Agreed? Cool. All right, nicely done. All right, let's talk about proper and improper fractions. First of all, heads up, I hate the term improper fraction. I don't think there's anything improper about it. Proper fraction. N over D. For a proper fraction, N is less than D. For an improper fraction, N over D, N is greater than D. I guess I had to pick some word. I don't know why they chose improper fraction. Here's what I don't like about improper fractions. 10 over 8 is an improper fraction. I also think it's a perfectly acceptable answer. Each piece is an eighth of the whole, and I've got 10 pieces sitting in a pile. The reason I don't like improper is because people constantly feel like, oh, well, I need to convert that. Capon thankfully gave us both. He gave us the improper fraction and the mixed number. But here's the problem with mixed numbers is that now if I want to do something with that mixed number, it's actually a lot of the time harder than if I had just left it as an improper fraction. So if you're done, I'd say that this is a really good final answer. But if you're in the middle of a problem and you end up with an improper fraction, I would just leave it alone and say, well, I'll convert it when I'm done. Again, there's nothing wrong with either of them. They're both perfectly good answers. Really, the question depends on context. If I wanted a bunch of sheets of maple or pieces of maple boards, yeah, it's probably easier to go into the store and say, give me one whole board plus 2 pieces versus going in and saying, give me 10 eighth pieces. But so I would say for final answer, that's a good thing, or depending on context, that's a good thing. All right. We're not going to spend a whole lot of time talking about proper versus improper. My goal is to not force you to do anything in a particular way. My goal is to get you used to working with fractions and be comfortable with the vocabulary and the notation. And so far, you're probably thinking, yeah, I get this. This is pretty easy. Hopefully you're remembering it if you didn't, and you're saying, oh yeah, yep. But it's also important that we have this background before we go too far. Because if I just bring these things up later, then you're like, oh, I don't remember what that is. Did I tell you about when I took the geometry class at college? So I graduated from University of Washington with my engineering degree way back in '89. Went off with the Navy, got out of the Navy, went and worked at a variety of jobs for about 3 or 4 years, went and became a Harley mechanic, was a Harley mechanic for 8 years, decided to go back and be a teacher. And so now it has been 15 or so years since I've thought about geometry at all. And to be honest, we didn't do a whole lot of geometry in the engineering program. So I could even argue that it had been 20 years since I'd taken geometry because that was high school. And I get into one of my first math classes down at Western to become a teacher, and it's a geometry class. And he's saying things like acute angle and obtuse angle. And I'm sitting there feeling like a complete and utter idiot. Because I'm like, oh man, I have an engineering degree. I'm, been doing stuff for 20 years and I have no idea what those words mean. So as soon as class was over, I went straight down to the Western bookstore and I bought a book called Geometry for Dummies. And I read the whole thing and I was like, oh yeah, that's what that is. So sometimes we just need a reminder when the topic pops up, and that way we don't feel quite so stupid when we're like, I don't know what that means. All right. Let's see. Writing improper fractions as mixed numbers. Yeah, I don't care. Do we care? Yeah, let's do that. Let's go back and forth because it can be useful to go back and forth. So let's start with 23/4. And we're going to go to a mixed number. So we're going to have a whole number and a fraction. And hopefully you'll just be like, oh yeah, I know how to do that. Step one, we got to figure out how many holes there are. 4 goes into 23 how many times? 5. Remainder? 3. Have the piece sizes changed? No. The piece sizes have not changed, so that will always just be the same number. All right? So why don't you guys do 31/4 and 27/8. Convert those to mixed numbers. I'll suggest, I see some of you've got your Chromebooks open, and try to do these in your head to the extent that you can. And the only reason I say that is because when you're on a job site, yes, you theoretically have access to a calculator, but it sure slows you down when you have to stop and get out your calculator or get out your phone every time you want to do a quick conversion. These are all going to be generally relatively small numbers. This is, again, why they sort of make you learn that 12 times table at one point. As you use them more, it'll get easier and easier and easier to keep using them. And you can really save yourself a lot of time once you get comfortable with the numbers by being able to just look at it and go, like you guys did with the 23. Oh yeah, 4 goes into that 5 times. Remainder 3. Ethan, first one.
7 3/4.
You in agreement? Cool. Jack.
3 3/8.
Agree? Ethan, you've got a frowny face on from what I can see.
My fault.
Just checking your own answer? Okay. Yeah, 8 into 27, 3 times remainder 3. 4 into 31, 7 times remainder 3. So now let's talk about going back the other direction. 5 holes. But how big were our pieces? 4s. Which means that I have 5 4s plus the remainder. 5 times 4 was 20, plus the remainder was 23. So if I think about it, what I'm really doing is I'm converting this to fourths and then adding it to the number of fourths that I still had. So let's do a quick example, and then I'll give you a couple today. 3 1/5. What are my parts? Fifths. 3 of those, 3 wholes, is going to be 3 times 5, which is 15, plus my remainder. So if I think about this, there's my wholes, there's my remainder, and I've got 16 fifths. Agree? Okay, your turn. Four 3/8. And 15 2/3. Bailey, 4 3/8.
35.
Say that again.
35.
We in agreement? Yeah. 4 wholes is going to be 32, plus my remainder 3. Good. Savannah.
47 thirds.
We in agreement? Yeah. 15 wholes made up of thirds, there's 45, plus 2 more for the remainder is 47 thirds. Good. Questions? We going just the right speed? Okay. Getting that refresher in, but not bored because it's so darn easy. And not like, oh my God, I have no idea what he just said. He's going so fast. Hopefully we're just optimal speed. All right. Now, let me give you a quick example of when we use fractions. I use these all the time in my motorcycle shop. Just a ruler. This is an inch. That's a ½ inch. That's a ¼ inch. That's an 1/8 of an inch. That's a 1/16 of an inch. This is a 32nd of an inch. And I actually have a machinist ruler that goes down to a 64th of an inch. I've done this long enough that I know, for example, that an eighth of an inch is 0.125. So if something says that something needs to be within 0.125, I know that's an eighth of an inch, and I can slap a ruler on there and I can see it. Whereas a ruler that goes by 0.125s would just be hard to read. The interesting thing is, I also know that that means that 2/8, well, 12 and a half doubled is 25, right? So 2/8 is 0.25. Something has to be 3/8 long, 12 and a half tripled, 36 plus 1 and a half, 37 and a half, right? You get good at this if you do it enough. You start to be able to just do these things in your head. You talk to a machinist who's been a machinist for 20 or 30 years, you won't see them with a little calculator constantly calculating stuff, because they'll look at the stuff they get a machine and go, oh yeah, boom, off they go. It's more complicated. A calculator might come out. But for basic stuff like I need 3/8 of an inch, they'll rock right into this and go, oh yeah, I know what an eighth is, so therefore I know what the multiples are. Okay. Let's take a look. It's simplifying. Guys, the first trick on simplifying is to figure out common factors. And there are some tricks to figuring out common factors, and I'll show you a few of the tricks. I may show you more of them as we go along here in the time we have. It's a nice thing about having a schedule where we can get to wherever we get to. It doesn't really matter. I can stop and go off on little tangents whenever I feel like it. And we learn what we learn between now and next Friday. First off, anything obvious that goes into 105 and 90? Do we agree that 5 goes in? Is that what you were holding up 5 fingers, not a hand?
No, it's holding with the hand.
Oh, okay. What were you going to say?
I was going to say that like 15, pretty much anything up to 15 that's a 3.
How do you know that 3 goes into that?
Because 9 divided by 3, and then
Okay, so the 9 one's pretty easy.
yeah, and then if you add 15 to 90, and
Interesting. So since 3 definitely goes into 90.
yeah, maybe.
Oh yeah, continue. Oh, to the bathroom. Sorry, I thought you were still going to continue with this. Yeah, go. Yep, absolutely. So that's a really interesting observation, and this is, guys, where patterns come into play. This is where seeing patterns. And one of the things I've noticed over the years is a lot of the time people that struggle with math, one of the reasons they struggle is because they don't see patterns. You see the word 9, I immediately think to myself, hey, I know that that's 3 times 3. But if you just see 9 and are like, it's 9, it's a lot harder to do math because you don't see, oh, look, there's a pattern there. Jack saw an interesting pattern. He says, well, I know 3 goes into 9, therefore 3 goes into 90. And that's 15 more than 90, so 3 must go into that one as well. Because 3 goes into 15. I like that. Now, do you need to see that? No. But those patterns definitely help. Here's another way to tell if 3 goes into a number. Add the digits. Divide by 3. If you add the digits and divide by 3 and it goes in evenly to the added digits, then it goes in evenly to the original number. 1 plus 0 plus 5 is equal to 6. Does 3 go into 6? Then 3 goes into 105. What are we freaking out about back there? We're seriously freaking out because a fly went by?
Yeah.
Oh boy.
Avenging its brother.
So, questions for you. 327, yes or no, divisible by 3?
Yes.
And you know because? Tell us.
3 plus 2 plus 7.
Is?
12. Which is back. 3.
12 is divisible by 3, therefore so is 327. 4,851, divisible by 3, yes or no?
Yes.
4 plus 8? 5 plus 1? 12 plus 6? Guys, notice how I split that up? Mental math is easier if you split stuff into smaller clumps. 4 plus 8 is 12, 5 plus 1 is 6, 12 and 6 is 18. Which means that 4851 is divisible by 3. What else obviously goes into 105 and 90? 5. Here's another little trick. If two things go into a number, then their product also goes into a number. So 3 goes in and 5 goes in, then 15 must go in. How many times? I want everybody to have a chance to think about it. How many times? What do you think? How many times? 90? 7 into 90? Agreed. I'd actually divide 15 into 90 first because of Jack's observation that 105 is one more, and 90 is easy to divide by 15, right? Because I know that 2 15s is 30, and 3 30s is 90, so that means I need 6 15s. And then I don't have to sit there going, 105 divided by 15. I just go, oh, it's got to be one more. Now, this is the deal I was going to get to when we were talking about algebraic fractions, the next algebra 2 thing. Because this is something that throws people a lot. I can write this like that, agreed? Because fraction multiplication is just multiply all the top things and multiply all the bottom things, which means I can take them and separate them if I just do that backwards. What's that equal to? 1. Agreed? So this whole thing can therefore be written as 1 times 7, 6. Remember, that's times, not 1 and 7, 6. It's 1 times 7, 6. Well, what's 1 times something?
7.
Itself. This is where people get messed up when we go back to thinking about algebra. Because if I were to tell you that 3 times, well, let's redo that one. Different problem. Can you cross out the 15s? Can you cross off those 15s? Yeah? Yeah? No? No? Yeah? About half and half so far. People going like this and people going like that. Ethan, why are you shaking your head no? They're not multiplying. If we think about this, do we agree that this is 22 divided by 21? Yes? But if I cross out the 15s, how do I make that equal to 22 over 21? It doesn't, does it? The only reason that you can cross off things that are on the top and the bottom is because you're rewriting it as multiplied. One way to think of this, if you want to think of this as PEMDAS, which I know we all love, this is a divide, right? But this is a parentheses, and this is a parentheses, even though we don't write the parentheses. It's something divided by something else. We have to figure out the something. We pretend it's in a parentheses. That's one way to think about it. And figure out the other parentheses, and then we can do division, because parentheses comes before division. So we want to be a little bit careful here. The whole point of reducing fractions is that we rewrite it so that it's 1 times something, and then we can cross off the 1. Right? We cool with that? Okay. Let's do a bigger number. You okay? Let's see. Do I have an example of a bigger number? How about 15 over 84? Not really bigger, just different. What goes into both 15 and 84? So common factors. Go. Andrea, common factor?
30.
Are there any more? Well, let's think about it. Does 2 go into both of those? No, because it doesn't go into 15. Guess what? We've just eliminated all the even numbers. We don't even have to think about even numbers anymore. So the next number to test is 3, which we've already agreed goes in. We don't have to think about 4 because we've already eliminated even numbers, right? 5? doesn't go into 84. Don't have to think about 6. 7. Well, we've already run out of things that go into 15, haven't we? Because the only things that go into 15, and we never care about 1, 3 and 5. So once we've checked 3 and 5, we don't really have to check any further. It's a little harder as the numbers get bigger. So we might want to do it in steps as the numbers get bigger. So I'm going to write this as 3 times 5 over 3 times 28, says Jalen. Are we in agreement? Guys, do you know how to do 3 into 84 in your head? 3 goes into 8 how many times? Remainder? 2, which means I'm left with 24, agreed? 3 goes into 24 how many times? 8. This is actually a process called short division. You remember long division? 3 into 84 would be like this. 3 goes into 8 twice, 6, 8 minus 6 is 2, carry the 4, 3 goes into 24 8 times, 8 times 3 is 24, remainder 0, I'm done with the problem. But it's a long, involved process. Short division, what you have to do is you just have to keep the remainder in your head and carry it over. So when you carry the 2, which was your remainder here, and you just say, oh, well, I would have brought the 4 down, and so if I had remainder 2 and I bring the 4 down, that leaves me with 24. You can actually go through some pretty big numbers in your head if you think of it as one thing at a time and just working your way across. All right, so this becomes 3 over 3 times 5 over 28. 3 over 3 equals 1. So this is 1 times 5 over 28. 5 over 28. Jack.
So I'm just thinking about this. So prime numbers are ones that can only be multiplied by 1 to get itself, right?
Correct.
Okay.
Yeah, prime numbers factor to 1 in themselves. 4,281 divided by 8,692. Here, let's do this. What's the obvious one? Common factors. Good. Is 3 a factor? Four plus 2? 8 plus 4? 6 plus 12? So 3 goes into the numerator. 8 plus 6? Yep. 9 plus 2?
11.
14 plus 11?
25.
3 doesn't go under 25, so 3 is not a common factor. 4? 4 is a little trickier. How do you tell whether 4 goes in? There's a trick. I don't remember off the top of my head. But one thing to do is just to divide that in 2 and see if you get an even number. When you divide that in 2, it's going to end in 2, right? When you divide this in 2, it's going to end in 0. So that means that 4 is actually a common factor, or should be. 5? 7? Here's where remembering all the tricks. The only trick I remember is for 3 and for 4. There's a trick for 7 and there's a trick for 11, and I can never remember them. So here's what we do. As we step down. So Ready? Here's how we do our short division. 4 goes into 4 how many times? Remainder? 4 goes into 2 how many times? What?
0.5. 0.
Doesn't go in at all. 0.5 isn't a goes into. Silly caping. Remainder? Four goes into 28 how many times? Remainder? 0. 4 goes into 4 how many times? Do the bottom one in your head.
What do we do for remainder? For the top one?
There is no remainder for the top one.
No, it says 4 and then 2.
Turns 8 into 28.
4 went into 2 0 times. Remainder 2. So I carried the 2, which gave me a 28. Then 4 went into 28 7 times. Yeah, all you're doing is you're doing the long division process, but not writing out the whole thing at each step, which makes it easier to do mentally. Isabella, 4 goes into 8 how many times?
Twice.
Remainder?
0.
Bryce, 4 goes into 6 how many times? Remainder? Ethan, 4 goes into 29 how many times?
7 times.
Remainder?
1.
Jack, 4 goes into 12 how many times?
3.
Not bad. Think about it. If at the very beginning of class I'd said, quick, no calculators, 4284 divided by 4 and 8692 divided by 4, we probably all would have freaked out and said, I can't do that, it's too hard. We just did it in our heads. Hey, what reduces?
The ones.
The ones. So what, those?
Yeah,
7.
well, the 1 and the 7.
What?
7.
The 7s reduce? So I'm just going to start crossing stuff off here.
Yeah.
So this is actually
10 over
10
23.
23rds.
Yep.
Seriously?
100%.
I think so.
Instant done. Instant win.
Guys, what did we say about what are we allowed to reduce and what are we not allowed to reduce?
4 over 4.
That's a 1, agreed? This becomes 1 times the rest. You can't reduce things just because they happen to be there. You can only simplify or reduce things because something divided by itself is 1. That's not technically a 7. That's a 7 in the 10 digits place. And just because it's in the same place doesn't mean it reduces and makes a 1. Otherwise, 170 divided by 70 would be what? 1? Or 100, depending on how you looked at it. Can't reduce those because we're not multiplying numbers together. It's just these are the places. 100's place, 7 10's place, no 1's place. Agreed? We go to that? So actually, this didn't reduce a whole lot, but still, I would say 1,071 out of 2173 is better than 4284 out of 8692. And I just made up these numbers. I didn't plan ahead and have numbers that would reduce a lot. I just said, oh, let's write down 2 numbers and see what happens. Okay. Questions?
Can we reduce it further?
I don't know. The only possibilities would be maybe 7 goes into those. Here's the thing about, I just remembered one of the tricks on 7. No, I didn't remember the trick on 7. 7 might go into those. 11, 13. I don't know off the top of my head. We would then have to do a little more plan. We could check. 7 goes into 10 how many times? Remainder? 7 goes into 37 how many times? How many?
5.
5. Remainder? 7 goes into 21 how many times? Oh, so this is actually 7 times 153. 7 goes into 21 how many times?
3.
Remainder? Into 7 how many times? Remainder? You already see the problem?
Yeah.
We're going to be left with 3, and 7 doesn't go into the 3. So, yeah, 3, 1, doesn't work. So, the tricks are nice. At some point, you run out of useful things to try, and you just move on. All right, let's do a little comparison. You got a 5/8 drill bit. And it's too small. Excuse me, it's a 3/8. And you got a 1/2 inch drill bit and it's too big. What size drill bit are you gonna try next? Jack?
Well, 6/16.
Where do you get 6/16?
Because you can't, because 8/16 is 1/2.
Okay, hang on. So you're saying that this is equivalent to an 8/16 drill bit.
That is equivalent to an 8/16.
That one is.
Yeah, and then the other one, wait, I said 6/16, I meant 7/16.
What's this equivalent to?
6/16, so I'm saying 7/16 might be your next try.
Does it make sense that it's a lot easier to compare if they have the same denominator? I look at 3/8 and a half and I say, I don't know. What's between 3/8 and a half? But it's really, really obvious that that's in between 6 and 8. So Hannah,
How do you get that?
how do we get what?
6/16, 3/8.
Because you multiply both by 2. So if you multiply.
So let's, hang on. Let's not just have one-on-one discussions. Let's have a class discussion. How do I get? And then the other question might be why 16ths? The least common denominator of 8 and 2 is actually 8s, right? Really? Is 8 common to 8 and 2? No?
No,
How many 8s is a half? So I could write this as 3/8 and 4/8. Why not?
well, you could, but it's,
Ah, stop right there. So in other words, it is a common denominator. To answer the first part of the question, do we agree that I could leave 3/8 alone and then just convert a half to 4/8 and say I got 2 drill bits and one of them is 3/8 and one of them is 4/8?
Yes.
Now, what's the problem? Because Jack has an objection here. What's the problem with saying 3/8 and 4/8? Corbin?
You still can't compare them. Because you can't just say 3/8, well, it's just,
You can't say 3 1/2 or 3.58.
There's the drill bit that's halfway in between, right? And there's no such thing as a 3.58 drill bit because it's called a 7/16 drill bit. And I never want to put decimals in a fraction anyway, because putting decimals in a fraction is just weird. Why wouldn't you just cut it into more pieces? All right.
But I mean, if you work with like standard sockets every day, you're gonna know what's in between those off the top of your head anyway.
Yeah, and that's an interesting observation that Andrew has. If you're working with sockets every day, you got a rack of sockets, and your rack of sockets has a 3/8 socket and a 7/16 socket and a 1/2 inch socket and a 9/16 socket and a 5/8 socket. And you get used to those. And you look at a drill bits and you say, I got a big pile of drill bits because some kid from the high school that I hired to clean up dumped all my drill bits in a box, darn it. And I root around and I find a 3/8 and it's too small, and I root around and I find a 1/2 and it's too big. And Andrew's absolutely correct. If you're using those all the time, you'd be like, wait, I know that 7/16 comes halfway in between these two. You wouldn't have to do all these calculations.
If you use the metric system, in general, you wouldn't have to.
Yeah, but for drill bits, metric systems suck.
Yeah,
They really do. They're a pain. There's weird sizes.
yeah.
They're all 1/2 millimeters, and it's
Yeah.
like, what? But yeah. So guys, the point of this problem is that to do comparisons, Jack,
Yeah.
listening please.
Yeah.
To do comparisons, we want a common denominator. And it doesn't matter what your common denominator is, you may have to then adjust. I would probably have ended up with 3/8 and 4/8 and said, well, we don't know what's between 3/8 and 4/8 because we want whole numbers. And then the second step would have been to go to 6/16 and 8/16. All right? Any questions? Okay. Let's do some just practices of these for a few minutes. And then tonight for homework, I want you to do part of it. I want you to do part A of the worksheet. Okay. Guys, if you've been sort of holding off and doing the homework whenever, try to get part A done, because if you're good at simplifying this stuff, if you're good at solving these problems when we come in tomorrow, this will be easier. All right. If you just don't do the homework, well, then when we get to multiplying tomorrow and we start to talk about simplifying, you won't have had any practice and you may or may not be any good at the simplifying. So let's do some comparisons. 3/2, 13/18, 13/8 rather. 3/16, 25/60. And 1 1/5, or 8/7. So I want you to figure out which one's bigger. Remember, no calculators. We're not just typing them into the calculator and comparing decimals. We're actually thinking about fractions here. Bella, what did you do for that first one?
I don't even know. I said that 6 I just like divided 3 by 2 and then 8 by 2 and 13 by 2.
What?
I don't even know.
What's the least common denominator of 2 and 8?
Uh,
Well, 8 is not the common to 2. So guys, here's the problem. If I make this denominator into 2's, then I'm going to get a decimal on top, right? And if I make it into 4's, I'm going to get a decimal on top. So I can't make this denominator smaller. I need to make that one bigger until they match. What do I need that one to be if I'm going to make it bigger so that they match? Good. And this becomes 12 over 8, agreed? Which is bigger? I suppose we could just all sit here until the bell rings and then not get to the rest of them. And then when you go to do homework, you'd be like, man, I don't really get how to do these. That's one strategy.
13.
All right,
No,
well,
no, like 30 seconds would be way too
really?
Well, 12, 33.
But I don't care about 3 over 2. I care about 12 over 8, right?
Yeah, that would still be bigger.
12 out of 8 pieces is bigger than 13 out of 8 pieces.
No. I lied.
The next one. 25/60.
How do you know?
Because it's way closer to half than 3/16.
That's not a good strategy.
Well,
You're just saying, I think. Too bad. I would have liked to get those, but I'm sorry we spent the last 10 minutes all sitting staring at each other and staring at the board instead of thinking and working.
Thank you.
Oh, well, do the first part of the homework. Have a good one.
I was gonna ask if we were doing more like 3D graphing stuff for tonight's homework. I'm glad that we aren't, because I'm not good at that stuff. Thank you so much.
That's a good one. That's a good one. Sometimes you gotta push the marker down the stairs to get them to realize how close he is to falling down the stairs. Mark always falls down the stairs. They're not falling down the stairs.
You won't be close to falling off the head. It is falling down.
Everything that I would have sometimes you gotta speak with authority to understand